Thanks. So yeah, my talk is Dancing with Attitude. I'll explain where the name came from. You might already know if you've had a look at CoreMotion before. But yeah, so this is just the same title slide again, not useful. But a bit about me before we start. I'm an iOS engineer at Canva. You might have heard a bit about Canva already from all the other Canva speakers that were here this week. But essentially, we're a design app, lets people make really cool, great looking designs with an easy to use interface. You can make all sorts of stuff in there. And yeah, you may be wondering why someone working on a design app is doing a talk about CoreMotion. And that's a really good question. So why did I want to do this talk? So a little known fact about me is that I really like rhythm games. I've been a massive fan since I was really young, like DDR, this kind of games. So movement and that kind of stuff always kind of struck me as really interesting. And I've always been really excited about CoreMotion since I first saw it in WWDC in 2015. And I saw the session where they introduced CoreMotion on the watch, and my brain was just buzzing with heaps of ideas of how this could be used, and it was something really cool that I thought we could have some, make some really great experiences with. And so when I was thinking of a talk for this year, I've previously done a lot of kind of technical architecture-y based talks, so I want to do something more interesting, and I thought that a combination of these two interests could be an interesting talk. Having said this, I'm definitely a novice at both of these things, so this was a learning experience for me, and hopefully you guys can learn something from what I've learned going through and getting stuck into these frameworks. So having said that, I did say that I was going to make a rhythm game in this talk. Turns out making a rhythm game is much harder than making a CoreMotion thing. It's really, really hard. So I won't be actually demoing the rhythm game, but I'll be demoing the components that we need to make it. Yeah, I do have a day job to do, so as much as I'd love to make rhythm games for a living. Cool. So the plan of attack for today. First, we're going to talk about what CoreMotion is and why we'd want to use it. Second, we're going to talk about the API that we have from Apple. Thirdly, I'm going to talk about gestures, what I mean by the word gesture, and why I think it's a good way of thinking about these types of problems. And then we'll go through some examples in code and hopefully a working demo as well. So, CoreMotion. It's a framework. It's provided by Apple, so no third parties here. It's all built into iOS and watchOS. And essentially what CoreMotion is it gives us access to a few things that the device knows about. So firstly, motion-related data. This is where the device is in space, how it's moving, and some environment-related data, which is kind of stuff that the device knows about outside of itself. So for example, where magnetic north is, there's a magnet sensor inside. Also where gravity is in relation to the device, things like that. And yeah, so it gives you access to the data from any of the hardware sensors that we can use. The sensors that we have access to, there are 5 on iOS. There's also GPS, which I didn't put on the slide, but that we won't be talking about today. So the accelerometer, the gyroscope, and the magnetometer. And you also have the pedometer and barometer, and all these have them are hard to say because there's lots of ohmmeters. But the accelerometer is detecting movement, or specifically the rate of change of position. You may have known acceleration from high school physics. Essentially, it only knows when the device starts or stops moving. It doesn't know when it's just kind of at a constant rate of movement or stopped. The gyroscope measures orientation in relation to the ground, so where gravity is, essentially. And the magnetometer measures the magnetic fields of the Earth. The pedometer and barometer. Pedometer measures steps. It's very specific to steps. And the barometer measures altitude. We're not going to talk about these two today. They're not really useful to our use case. So to give you an idea of what we're trying to do today, we're going to be we're trying to detect when the user does specific dance moves. And maybe you could have a dance move that's like a step, and the pedometer could be useful, but it's kind of too specialized for the types of movements that we want to do today. And the barometer is not really accurate enough. It doesn't provide high fidelity data that could be useful. It's relative accuracy is about 50 centimeters, so it knows if you move outside of that range, but a lot of the movements that we would do are quite a bit smaller than that. All right, so the accelerometer, this is a big one. This measures changes in velocity along a specific axis, and it's measured in G's. 1 G is just the acceleration of gravity, and the way that this sensor works is there's a 3-axis accelerometer inside the device that tells you in 3D space how you're moving. And the important thing to note is that the accelerometer data that you get out also contains the acceleration from gravity. So if your device is sitting on the table, the acceleration isn't 0, it's actually down at 1g. And you have to take that into account when you're kind of using this data. So the kind of visual representation of what that looks like. The way that it's reported is in this different orientations. So the y-axis is through the top of the phone, z is through the middle, x is side to side. And so if you were to rotate the device in space, you would end up having these axes actually move. So if you want to do anything about absolute movement, you have to know what orientation the device is as well as the acceleration. And that's where the gyroscope comes in. So the gyroscope measures the rate at which it's rotating around an axis. And same as the accelerometer, we have a 3D gyroscope in the phone. Measured in radians per second, this can easily be converted to degrees if you prefer to work in degrees, but you have to remember which one you're in. Don't make the mistake that Paul was talking about yesterday with the units. And yeah, so the gyroscope does essentially rotation, but it's important to realize this measures the rate of rotation, not the actual fixed rotation in space. Very similar to the acceleration, you have the 3 axes. You can use the thumb thing to figure out which way positive is, but it's usually pretty easy to figure out. So, the last one is the magnetometer. This measures magnetic fields. It's mostly used to detect the Earth's magnetic field, but it will actually be affected by local fields within the device and nearby. This actually got me kind of excited because I was thinking that would be really cool if you could have a magnet-based game controller that you kind of move around. Turns out it's really bad to put magnets near your phone, don't do that. If it goes too close, the magnetometer actually can't read the values because it's too strong a field. And it can also screw your compass forever, or for a very long time, if it magnetizes parts of the phone. And also, obviously, magnetic fields near hard drives and things like that is not a great idea. So these are the sensors we have to work with, but how do we access the data from them? So we can talk about Apple's API for this. The first thing you need to know about is CoreMotion Manager. This is sort of the access point to CoreMotion. It's where you start and stop any updates from any of the sensors, and it has 2 types of API. It has a pull-based API and a push-based API. And so which one of these you use will be dependent on the type of application that you're creating. The pull-based API, you start updates, and at some point in your app later, you can read these updates out. And a type of application that might use this is something like a game or something where it's real-time updating some UI. So you need to essentially get an update per frame. In that case, you might want to put this line inside your rendering loop, something like that, to make sure that it's always updated for the current frame. The push-based API will give you updates at some frequency, and it pushes you the data via this closure here. It takes an operation queue, which is the queue to perform these closures on. It's really important to not use the main queue for this, because this could be called, and I think the default is 60 times a second, and if your handler does anything at all computationally expensive, this could block your UI, and you really don't want that. So always use a separate queue, and make sure that you get the data back and also an error. You can look at the APIs to see more details about that. So you can see in these 2 slides I've used the accelerometer updates function. This gives you the raw accelerometer data, which is kind of just lots of numbers. It's got all the gravity in there. There's bias in the device. You could be on a train and your train's kind of moving and slowing down. So there's a lot of stuff you have to take into account to actually use this in a useful way. And so you could use it directly, but you'd have to do a lot of work. So Apple actually provides a kind of combined API that gives us bias, but essentially a fusion of all the sensors to remove the bias due to gravity, other environmental factors, like I was saying, magnets nearby, being on a train, that kind of stuff. So it kind of smooths out the data, makes it much more easy to use. I would say always use this over the raw data unless you know what you're doing. If you knew what you were doing, you probably wouldn't be at this talk, so probably use it. It's actually a really easy to use API. and it essentially gives you pretty much better data than the raw data in all cases. So this API has a few different things it can give us. It can give us the orientation in 3D space. This is really cool because the only way to get this is to combine a lot of different data together. So you'd have to use, for example, the accelerometer as well as the gyro together to try and get this, because they both measure rate of change. They don't actually measure the absolute position. So it gives us the orientation or attitude, which is where the name of the talk came from, and it gives us that relative to a reference frame, and we'll talk about that in a minute. So it also gives us the unbiased rotation rate. So this is kind of, if you're moving back and forth, up and down, it'll give you the rate of rotation. The current gravity vector, so where gravity is, and this is actually super useful for most of our use cases, so we'll talk about that a lot later. And the user-generated acceleration. So this is actually taking into account gravity and removing it from the sensors, which is super useful as well, because we don't have to want to subtract gravity ourselves every time. Lastly, it gives us the current magnetic field vector, which is essentially our heading relative to north. We won't be using the magnetic field stuff today, but we will be using most of the others. So reference frames. So these are the things that you give to the CoreMotion when it starts to say, this is where you should calculate your attitude or your orientation from. Don't worry too much about these. You can look up the differences between them if you like. But we'll be using the first one, which is the default, which essentially says, if the phone is flat like this, then Z is the vertical axis. And so if we were to use this reference frame, the device was sitting flat on the desk, we would get 0 for all the values for rotation. But if we were to start like this, we would have like 90 for one of them, 90 degrees, and then 0 for the others, example. So it's really important to keep in mind what orientation you're in. But the other ones, just for interest, the magnetic north just means that it's calibrated to always point X to the north, which for something like a gesture-based game doesn't make much sense, but maybe for if you're doing a AR style thing in a room, you want to know which direction you're in, that's kind of important. Cool, so some quick tips for CoreMotion. Firstly, some sensors require authorization, particularly GPS, magnetometer, in some cases. This is because it's essentially giving you personal data about where the user is, so you want to be making sure the user knows that. But if you use device motion and only use the arbitrary XZ vertical reference frame, it won't need authorization because that's not identifiable to the user. Anytime you use a magnetometer, it may ask you to calibrate it. I don't know if anyone's seen this thing where you have to do like a figure-8 shape to try and calibrate the magnetometer. You might see that. It's a little bit weird, but for our purposes, not necessary. You should always check if the sensor is actually available on the device. Some devices don't have all the sensors that others do. Particularly, like the watch will be able to do everything except the magnet stuff, or older devices don't have an accurate enough gyro to do the device motion thing. So you should always check that it's available and configure your capabilities for your app so that if you require a gyroscope, you aren't letting people use your app that don't have a gyroscope, because obviously it's not going to work. And again, don't use the main queue for updates. You block your UI and no one likes that. Cool, so gestures. I want to talk a little bit about what I mean by gestures in this case. You probably are familiar with touch-based gestures. So when you're on your phone, you swipe, pan, pinch to zoom, those kind of things. We use those gestures every day. And actually, this is quite similar conceptually, but you might have to think about it a different way when trying to build them. So some examples that you might have seen, racing games that use tilt controls to do the steering. That's a lot of rotation. You might also have games that have like a bump to jump sort of thing, or tilting the device side to side to rotate a character. So that's some examples that you might have seen in the wild. And I think of each of these as kind of different types of gestures. So to get started, we're going to pick a song to get some dance moves from. Sorry in advance. I won't secure with this, but hopefully you know what that song is. The song is Never Gonna Give You Up by Rick Astley. There it is. I did take this as a massive excuse to rickroll an entire room of people, but I thought there were some cool ideas for moves in this. The chorus goes something like, never gonna give you up, never gonna let you down, never gonna run around or desert you. So I've got 4 moves that I've come up with from that. Let's go back to the slides. So the first one, never gonna give you up, simple move, just kind of moving upwards into the air. And the opposite for let you down, move it down. Run around is gonna be like a bit of a spin, and then desert you is like a point towards the person you're singing to. So these are the gestures that I've decided we're gonna do for this talk. And let's delve into how we're gonna build these. So to start with, let's have a look at the project. So I'm just gonna give you a quick overview of how I've set this up. I can find where the screen is hiding. Yeah, cool. So, all right, let's get rid of these and this. Okay, so this is a really, really simple app. It has one view controller that has a single label in the middle. I can't show you in the simulator because it requires sensors, but trust me, it has a label on it. I will try and plug my phone in and attempt to quick time it for the second half of the thing, but I'm not sure I can do that while on screen recording, so we'll figure that out. So, important things to note. Might make this a little bigger. Cool. So we have our motion manager. This is the kind of entry point to CoreMotion. You should only have one of these per app according to Apple as a kind of efficiency thing. I just have one for the view controller, and that's the only view controller, so that works for me. I have our queue, so this is our background queue to run those closures on. And I have an array of gesture recognizers, and I'll explain how I define that in a second. So the way this app works is whenever you tap the screen, it'll start recording for 1 second. And during that second, it will check for all of our gestures. And if it recognizes one, it'll update the label to show the gesture that it recognized. So super simple, but a great way to be able to quickly test different gestures and iterate really fast. The important function is this one, start updates. It first checks if the device is available, device motion. This is essentially checking whether it has all the sensors required. We have an update interval of 60 times per second. This can be up to 100 and as low as you want. So essentially, you probably want to pick something for something like this, you want it to be quite high because we want to have quite accurate motion. But for something else that's just detecting, say, rotation over time with a much less kind of time-sensitive thing, you could reduce this to a much less frequent update interval. So I'm using these start device motion updates with the block. In this case, it's really kind of a style thing in this case because I could every frame check if, I mean, it's essentially equivalent to starting it and then starting a timer every second that, or every 60th of a second that checks the value. But I think it's nicer to be able to have this backgrounded for me and kind of magic. Let me just mute this. Okay. Cool. So the important thing is that you get back some data. First, you check if it's valid. It's nil if it's invalid. And the data has a few things that you can access, and I'll go through those in a minute. But essentially what I'm doing is just updating each of the gesture recognizers with some motion and the duration since the last update. And now I could use 1/60th of a second, but that's not actually accurate because each time it could be slightly less or slightly more. So to get more accurate updates, I actually calculate the amount of time that's passed in between each update just by checking the timestamp. Each one of these actually has a timestamp already built in. You don't need to generate one. So that's super useful. All right, so really simple. Updates the gesture recognizes every time it gets new data, and then when after a second's passed, it just checks if any gestures have succeeded. So let's have a quick look at motion gesture recognizer. So this is a protocol. It's pretty simple. It just has an update with our motion and the duration since the last update, and then a function to check whether a gesture has happened. Cool. So that's our basic setup. That's what we're going to start with. Let's have a look at each of the gestures and kind of how we can think about detecting them. So we're going to start with the runaround gesture because I think it's the simplest one. It's kind of this moving around in a circle. We want to detect when the user makes a full 360-degree rotation, or close to. It's important to remember that you can't be too accurate with these things because the sensors themselves aren't that accurate. And also people aren't that accurate. If I run around in a circle, I don't really know exactly where that's going to finish. So it's important to be generous with your gestures, particularly because both people are different and also the device sensors aren't that accurate. So with this one, it's actually pretty simple. We want to detect when the user makes some rotation. Cool. So the give you up and let you down one's pretty easy. We've got the device, it's going up, it's going down. Simple to think about, but it's actually really hard to detect this. We'll talk about how you can go about it in a minute. But the important part to note is that it's in the direction of gravity. And that is pretty much the most important thing to take away is that if you can reference your gestures around gravity in some way, if they're not rotation, if they're a translation gesture, then you really want to make sure you can reference it based on gravity. And lastly, the desert U pushing forward, it's translation again, but it's perpendicular to gravity in a direction. And we'll talk about the pros and cons of using the approach that we'll use when we get there. So quickly before we jump into the code, I want to talk about some maths. Don't be too afraid. The maths here is pretty simple. Acceleration and gravity are given to us in a 3D vector. You have x, y, and z, each one's a double, and they're both in g's, so if it's gravity, it's just 1.0 in one of those axes. And essentially, if we can, one thing that we really need is to be able to find how much of our current acceleration is in the direction of gravity. And so there's a thing called the dot product of vectors, which is actually really simple to code, but hard to get your head around if you're looking at diagrams and trying to do the math part. But really, it's just, I'll show you the implementation. It's super simple. But good thing to know is just that we can get the amount of acceleration in the direction of gravity. So let's go to the code and have a look at some of our gestures. So this is our motion gesture recognizer, and each of our gestures implements this protocol. So, I don't know why that's opening on the other screen. Anyway, so let's start with the run around gesture recognizer. This is our rotation gesture that we were talking about before. So quickly, just to show you why I'm using this other type here, I've created my own vector type. It's really simple. It's just a type with 3 values, x, y, and z. And I've find some operators here just to be helpful. You can do this all manually in your code if you want. You don't have to create a whole separate type, but it just makes it a bit easier to read. So the important one to note is this one. This is the dot product operator. It's just 2 dots. I tried to use 1 dot, but Swift wouldn't let me. So 2 dots will essentially give us that dot product I was talking about before, the amount of that vector in the direction of another one. And so it's really simple. As you can see, you just multiply each of the components. Super simple. We also have an easy way to make 0, an easy way to get the length, so the magnitude of the vector. Cool. So first thing I do is I just pull out the gravity and the current rotation rate into those vector types. And it turns out that we can just do 1 dot product in the direction of gravity for our rotation, and it'll give us the rotation rate around this axis, so the vertical axis down to the ground, rotating this way. We don't really care which direction they rotate in, so when we check the value, we just absolute value it, and that way it doesn't matter which direction. So each of these samples gives us the rotation rate and the amount of time. And so if we want to calculate the total rotation, we just have to go through each of those and add them up. So we can add up the rotation rate times the duration, just so that we normalize it around the time, and gives us the total amount of rotation. And this is in radians, so a full rotation is 2 pi radians. But because as we said before, we don't want to be too specific, we want to be a bit more general, I actually use just 2 for this value. So if you go kind of a bit past half, that'll count as a turn. So each of the gestures follows a similar pattern. So in the update function, we'll buffer up a heap of samples of the values, and then when we're ready to check for the gesture, we kind of do some processing on those samples. Cool, so that one's really easy. The name's just used to print it on the screen. So let's just see if we can get this one to work. View controller. Cool, so I'm just going to turn off the other ones for now. And let me plug this in. Now, I actually wanted to do all of these using the watch, but the watchOS 5 beta bricked my watch, so I can't, sadly. Okay, now, this may work, or I may pull the phone out of the cable, we'll see. All right, so spin around. You can see, it says run around. Now, if I tap it and do nothing, nope. So it's actually detecting that rotation gesture via, doing those updates and processing it. So that one's super simple. That's, I think, the easiest one out of the 4. So let's move on to one that's a little bit more complicated. These two are actually exactly the same code almost. The only difference is that the threshold is negative or positive. So it's going up or down. So let's have a look at this one. Cool. So I took 2 approaches to this originally. I've actually left some of the code for the old one in there, mainly because I'm lazy and was rushing to finish this presentation, but it's actually kind of illustrative of the different ways you can look at these things. So for the rotation, it was actually really simple to figure out which variables we should use to figure out the gesture, but for something like this movement, it's actually not so simple. There's a lot of things that we could try and do. We could try and get the acceleration, we could try and figure out if, hopefully the device isn't rotating too much, but we should be able to count for that. Because we've got gravity here, we might do this. I think the first thing I thought of was, I could actually calculate the position of these things over time. Because if we have acceleration and we know how long it's been since our last update, we can, I don't know, if you think back to physics, it was like the acceleration is velocity times time, velocity is position times time. You can kind of integrate backwards and get position from acceleration. Now, I tested this a lot, and I've got some code in here that does that. It just essentially does those 2 calculations. It does adds the velocity, acceleration times duration to velocity, and then the same with position. This was semi-accurate sometimes. The main problem with this is that every time you do this calculation, any errors in the previous one are magnified. So while acceleration is very reasonably accurate, velocity gets less accurate, and then position is even less accurate than that. Over very small timescales, and if you're using kind of other data to try and figure out position, you could get away with it. But for something like we're doing where it's quite a small movement, the noise in the accelerometer was too much to be able to do this. So I had to think about what's another way I could detect this. And so thinking about the movement in your head, you think like, what's the acceleration actually going to do? What's the curve look like? And you can actually get apps that do that for you. They'll print out, you can do some movements with your device, move around, and it'll print out a graph of the acceleration over time. And those are super useful for testing out where you can get the data from. So for this one, I know that at the start of the movement, there's going to be a large amount of acceleration upwards. At the end of the movement, there's going to be acceleration downwards to stop again. So really, we just care about, did they move upwards? We really don't care about the stopping part. So the way that I've done this is I get the sample of each acceleration. So I keep adding these accelerations along the gravity direction. So as you can see, we're using dot product again. I'm multiplying it by 9.81, so it's in meters per second, not Gs. Reason for this is just the numbers are easier to parse. If they're kind of, I just like it better. But you could leave it in Gs if you want. Essentially, the idea is you get like a rolling average of the things. So I check the first 10 samples and see if the average acceleration was high enough in that positive direction. And if it was, I assume, yes, there was a gesture. To try and fix it around the case where they wait a minute before they start. I kind of move that average along and see if after 15 samples, is it now the gesture? And keep doing that up to the end of the samples. The reason this works really well is that at the end of the gesture, you slow down. And so the average kind of goes towards 0. So you'll never have a case where it just keeps going up or something like that. So yeah, this took a lot of trial and error. And there's something I think I want everyone to take away from this. Is if you want to work with, and this is the same for touch-based gestures if you're doing something custom, doing a lot of experimentation is really how you get to a good approach. With these things, especially things like these thresholds, there's no way you can just know that or figure that out programmatically. You kind of have to just pick numbers and see what happens, or look at the output, look at the numbers that are coming out, and pick something that works with that. So the give you up and let you down recognizers are the same. The only difference is that threshold is negative, and it's a less than sign here. I could probably make a reusable thing for both, but in the interest of time, let's see if it works. Cool, so this should do both the up and down. Fingers crossed. If I move it up, it says give you up. Pretty good. If I move it down, let you down. If I do nothing, it says let you down. There's a bug somewhere.
It let you down.
It let me down. But at least I can determine the difference. So it's one of these things where these thresholds are, I think I've lost my screen. Oh, cool. So these thresholds are something that even now I still haven't got 100% right. And it's one of those things that you just have to try it and do a lot of trial and error. And I imagine if you were doing some of these things in production, you would spend a lot of time on this phase, just testing things out, trying different values, seeing what works, what doesn't. Cool, so let's look at our last gesture. Now this one, as we said before, is also translation. It's very similar, but it's in a different direction. And now we know from those reference frames that we don't know which way the user was facing when they started. We just know that it's some arbitrary value in the rotation space. So being able to detect if that movement is forward versus sidewards, backwards, is actually really not trivial. And there is a few different ways we can get around that. I actually haven't done them here, and I'll tell you why in a minute. But just to give you some ideas, you could use the heading of the magnetometer on the phone. The watch, you don't have one of those, so that's a bit harder. But using that heading could give you kind of this initial direction, and if you're within some threshold of that, maybe that's how you detect it. You could also, sorry, yeah, that's probably the easiest way to do it. But let's have a look. So this one's a little different in that we need to get the acceleration that's not in the direction of gravity. So in this case, I was trying to figure out, can I rotate the gravity vector to be the right direction, all this crazy stuff. And then I realized that it's not that complicated. All you really have to do is get the total acceleration and take away the amount that's in the gravity vector, and then it should be what's left over. And you also want to make sure that the the magnitude in the direction of gravity is not too high, because you want to make sure that it's in this plane and not moving up and down, if that makes sense. So in this case, I'm detecting the maximum acceleration in this plane in any direction, and I'm detecting the maximum vertical as well. And I just check that they're both within the thresholds that I expect. So in the case of the vertical, I want to make sure that it's below a small number. In this case, I'm using probably, oh, sorry. That was my last approach. I actually fixed something in this just before the talk. And essentially, I've realized that all I need to do is figure out the difference between these two things and figure out if that's above the threshold. So in the case where we're moving up and down, the difference is going to be 0, or very close to, because it's in the direction of gravity already. So that's really good. And for the cases where we're in this plane, then the difference will be hopefully quite high. So all I have to do is get the difference and check if it's above threshold. At the moment, the threshold is 2 meters per second, but that was another thing where I just had to play around with it, find out some numbers. So finally, let's see if it works. How am I going for time, by the way? 1 minute? All right, cool. This is the end, don't worry. Let's try this last one. Cool, so now if I move the device forward, we get the desert U action. If I do nothing, we get nope. So I'll be around with this device on my person. It's my phone, so I hope so. If you wanted to have a little play with those gestures, feel free to. And yeah, so that's kind of an example of some of the gestures that we can do. And if we go back to the presentation. So that was a fair bit of code. I'll put this up on GitHub. Feel free to kind of have a look and see how I've used things. Play with the numbers yourself. I really urge you to try out CoreMotion. It's a really cool API. It's kind of confusing because if you just got a heap of numbers, what do you do with them? But there's a lot of stuff out there to help you out as well. So there's some really good WWC talks. There's some really, really good Apple documentation. They do a whole suite of articles on their docs outside of just their technical docs, which is really cool. The first thing is don't try and be too accurate. These things don't work very well if you try. Because there's just so much error in the sensors. So you want to be as general as you can with your movements and also have a lot of thresholds to allow for differences in movement. And it's even differences in people. If someone's twice as tall, the gesture is going to look very different to someone who's a bit shorter. Gravity is your friend. This is something I found I didn't really think would be a thing before I started this, but turns out you can use gravity for a lot of things. And it gives you a way to orient yourself in space. And that's something that you don't really have just from the sensors alone. And lastly, just experiment. This is one of those things where there's so many possibilities, I think. And I'd love to see more apps take advantage of these sensors because a lot of apps, there's not that many like interesting uses of this out there in the world. So hopefully you've learned something today. And thank you very much.